Okay, so I just started recording. Welcome to the Crowd Science Seminar. These seminars cover a broad area of human-AI collaboration to allow discussing past and future work, exchanging ideas, and establishing new collaborations. Today, we have a very special session dedicated to the NeurIPS conference that took place last week. NeurIPS is a flagship machine learning conference that featured more than 2,000 papers this year, which is huge. Alexis Rudza and Alexey Volobuev from the Toloka team will discuss the selected NeurIPS papers and share their perspective on the trends of crowdsourcing research. Let me present the speakers first. Alexis Rudza is responsible for data-driven decisions and the ecosystem of the Toloka crowdsourcing platform. His research is published at ACML, NeurIPS, Wisdom, and other top-tier conferences on machine learning and artificial intelligence. He is also a co-author of tutorials on efficient A/B testing and crowdsourcing, as well as an organizer of the Crowd Science Workshop at NeurIPS 2020. Alexey Volobuev is a machine learning research engineer at Toloka. He is also a PhD student at the Institute of Information Transmissions Problems at the Russian Academy of Sciences. Research interests of Alexey include general machine learning and additive combinatorics. So I'm really happy to give the stage to Alexis Rudza right now.
Sorry. Hi, everyone. So let's start our seminar. I remind you that we treat our seminar as a working seminar or a standard seminar that you can meet in maybe some research groups. Yeah. Somebody would like to ask? So maybe this is an issue. Okay. Therefore, feel free to ask any question during our talks, because they are not lectures or very big presentation, but rather than a discussion among us. Today, as Dmitry said, we present some selected publications related to crowd science that has been presented at the last NeurIPS conference. Here you can see the list of 6 papers that we have selected and that we believe are very relevant or important to know in crowd science. For sure, there are other very beautiful and awesome papers that have been presented at NeurIPS. But this is our view what is important, and we will present such papers. One thing is that important to know that since we have less than an hour to present 6 papers, so these presentations will be rather than overview rather than a pure deep dive in these papers, because each paper deserves its dedicated seminar talk. We will definitely invite speakers from those papers, and I guess four of them already agreed to give a talk at our seminar. So we will definitely be able to make a deep dive in each of these papers in near future. And for now, we will just present you some very short overview, snapshot maybe, just to motivate you to read this paper if you are interested in one of the talks, in one of the presentations that we give, and maybe further reach the authors of this paper then when they will give talk at our seminar. So before I will start presentation of the first paper, I will just emphasize that in the last NeurIPS conference, we observed a growing trend of considering crowd science or data labeling aspects of machine learning. This growing trend for now is observed in tutorials and workshops, and I believe that in few next years we will observe some.
Ma soprattutto manca qualcosa BDL.
Sorry, Dmitry, can you please mute our participants? So thank you. So I believe that we will observe much more paper than currently we consider in our seminar. So let's start. First of all, if you want to learn something connected to crowd science at NeurIPS, then you can reach this tutorial. So we can find a tutorial devoted to human labeling in NeurIPS conference, and for sure there are a lot of workshops at this NeurIPS that you can attend and read some outcomes of such workshops. One of them was organized by me, Dmitry, Daria, and Olga and Fabio. I will talk about this workshop a little bit later. So let's start. The first paper that I want to discuss and present is titled as Second Order Back-Bayesian Bounds for the Weighted Majority Vote. What are the contributions of this paper? First of all, the authors mention that majority vote, in fact, is a very fundamental technique, surprisingly, in machine learning models and approach to build very robust and state-of-the-art machine learning systems. In most cases, combination of different models via majority vote results in best machine learning systems that win competitions. The main important property of majority vote is that the majority vote in fact remove errors or effect of errors in the predictions by averaging them out, such errors. And this particular study has the following contribution. First of all, they propose second order Bayesian generalization bound for the weighted majority vote. And secondly, they provide some practical things that are connected with the weighted majority vote. Let's very slightly consider the setup. So the setup is very simple, very familiar for the most theoretical works on machine learning. Imagine that we have some set of hypotheses. Hypothesis is just a function from an arbitrary space to a finite one. Imagine, for instance, binary classification. We usually exploit in classification a loss function of the following form. When we talk about some theoretical guarantees about such loss, we usually consider expected loss. So we assume that our data are distributed according to some distribution D, and then we just take the expectation. When we talk about empirical results, we consider empirical loss for a given sample. So for sure, empirical loss is just the average of losses over the data. When we talk about possible models or classifiers or aggregation of hypotheses, one of the way to combine different classifiers is to combine them in a randomized way. So we just, for instance, if you have three classifiers, you take some probability distribution over such classifiers, and then you just flip a coin decide which classifier it wants to take in this particular sample, in this particular example, calculate the prediction and get the result. So for sure, expected loss for such classifier will be of the following form. Another way to aggregate classifiers, if you have several classifiers, is the majority vote model. It is very simple. You just find the answer, the answer that get the most number of votes during the prediction, and they select the answer. Okay, when we talk about theoretical analysis, we usually want to optimize. We usually want to have some aggregated loss that we want to optimize during our training process, for instance, or hyperparameter tuning. For that purpose, we usually try to upper bound very difficult to, we want to optimize the true loss that in fact we cannot, or it is very difficult to optimize by some empirical things. For instance, when we try to get optimal classifier of the following form, we need to optimize this loss. But this loss is very difficult to optimize due to the nature of the definition of majority vote classifier. But we can observe that this majority vote can be upper bounded by the following probability. So this probability means that if we have an error, then it means that at least a half of classifiers made an error on this example. Given this probability, we can use the first order Markov's inequality. I just remind there, and we can get the following final upper bound. So this upper bound can be much more easily optimized, since this is the expected loss of randomized classifier, not the loss of majority vote classifier. The main issues of this standard approach are the following. First of all, this issue ignores correlation of errors, the key power of majority vote, because majority vote is connected with correlation of answers. And for sure, this error, I will not give details because we have no time. This error also have some technical issues when we try to realize in practice. You can read about that in the following paper. The authors of this paper propose improvement of this upper bound. They also use the same idea to upper bound, to make the first upper bound of the expected loss of majority vote. And but they use the Markov inequality of the second order. This idea is very simple. So this is the core thing why the paper is very fantastic. So they use very simple, well-known result in probability theory. So just return back, see that this is very known inequality in probability theory of probability. The same is this inequality. So we have also very well-known inequality that has not been early applied to majority vote expected loss. They apply this very famous inequality in probability theory and get novel results, very fantastic novel results. Applying this approach, they get estimation or upper bound for the expected loss of majority vote in terms of so-called tandem loss. Tandem loss means that we treat the loss only if two classifiers have an error on the same sample. So therefore, we get the following upper bound. And the authors explain why this upper bound is better than the previous one, well known for the studies of majority vote. Also, they describe a special case for binary classification. So when we talk about binary classification, in this case, we can decompose this tandem loss in two parts. The first part is a standard randomized classifier expected loss minus expected disagreement of weighted randomized classifier. The key power of this summand is that you can measure this component without using labeled data. Why it is possible? If we talk about general classification, then we have to consider several classes. So we cannot expect, so we have to know information about which labels has been assigned by each classifier. But when we talk about binary classification, so when we have two classes, in this case, it is very easy to decide whether we have observed the disagreement between two hypotheses or not. And thus, since this term can be measured or evaluated without any labeling data, this term, in fact, can be estimated with high accuracy without requirement to collect a lot of data. So it is very important thing for optimization techniques of machine learning systems. So if we talk about some machine learning systems that we want to apply and optimize with respect to this loss, so the suggestion is the following. Ideally, you want to optimize this loss, but instead of this hard to optimize loss, you use to optimize this upper bound loss. And this upper bound loss can be optimized in a much more easier way and much more accurate way than the previous first order loss. For sure, when we talk about real practice, this part cannot be optimized by means of some algorithm, because this is just continuum system of samples. But in the case of optimization, we usually consider some fixed sample, but this is usually a standard technique. So if you have some expected loss, there are ways to get an empirical estimation. So the authors did this work and they obtained such formula. So there is no need for now to understand the components. The most important thing is that this optimization approach allows to take correlations of errors into account. It is very easy to minimize, and this upper bound is very tight to the ideal optimization goal. Okay, the authors provide several empirical evaluation results. They provide test errors of optimization over several data sets, and they show that their optimization with respect to their upper bound provides much more better classifiers than standard classifiers like majority vote without weights. So what way they optimize? They try to find such weights of majority vote in order to optimize or find the best classifier. And we see that optimization of the upper bound that they provided in this work results in a much more better classifier. Okay, what are the takeaways for crowd science for us from this work? So just remember that majority vote is not only a technique from machine learning, but it is the famous aggregation method in crowdsourcing. You just need to think of hypotheses as performers. So, and for sure, there is a lot of correlation between performers. So it is very natural to try to improve techniques taking into account some correlations between performers because, for instance, they read the same instruction, they pass the same trainings. And for sure, this work may allow to boost some research or practical algorithms that we can use in crowdsourcing. So you can ask me, if you can interrupt me in any time, but for now, I guess it is a good moment to ask maybe one question about this work.
Questions, please?
If not, I will just...
I have a question just to clarify. So is it correct that this paper was devoted mostly to machine learning,
Yeah.
Aggregation of multiple classifiers output, but it's not designed entirely for crowdsourcing aggregation, right?
Yeah, for sure. Yeah. The work is designed purely for machine learning systems. Therefore, was very surprising for me to find such fantastic work. I believe that this is a very fantastic work because it is improvement of already known method in crowdsourcing, and I have to find it's not by using very standard terms or keywords while listing the papers. So I just found this by chance. So
what really always made me interested or maybe curious is the fact that, for example, in the paper from 2009 by Jacob Whitehill about the GLAD model, they say like you can apply this model for aggregating responses from classifiers, not from the crowd annotators. So this is the opposite process of doing,
yeah.
Either you aggregate machine learning models or you aggregate crowd judgments.
Yeah.
Okay, so I think, do we have more questions on this paper?
Okay, let's just move next. So as you see, I spent a lot of time non-uniformly distributed over the works. So the next works I will just briefly introduce in a very snapshot. Do you see my screen or not?
Exactly.
Yeah. Okay, so the next work is about adversarial crowdsourcing through robust rank 1 matrix completion. This problem setup is very simple. Imagine that you have some matrix, for instance, if we consider crowdsourcing, imagine that we have columns connected with workers, rows connected with tasks, and matrix is filled by the information how a worker executed a particular task. You can understand that such matrix is not fully completed. So there are absent spaces because not all workers executed each task. So formally, it can be considered that we have some metrics. In this matrix, we observe some locations. So some elements of such matrix are observed. And we want to restore the initial matrix. For instance, such matrix in terms of David-Skin single coin model can represent how which quality was applied by a performer to execute such type of tasks. And so David-Skin model can be considered as such problem. And imagine that even if we want to restore matrix M, so the quality of provided results in the quality or skills of workers, we also have some unknown arbitrary perturbation of such matrix, or even it is not arbitrary, but some coordinated attacks of several workers. So, and authors of this paper proposed an algorithm to how reveal the skills of workers and the quality of the results in tasks. And so the algorithm is presented here. You can see that it is very simple. And for such algorithm, they provide several guarantees to recover. First, they provide sufficient and necessary conditions to recover the original matrix. And they also state that this algorithm will be optimal when we pick revealed elements of this matrix randomly. This means in terms of crowdsourcing that if you assign workers to tasks randomly, in this case, this algorithm will be optimal to recover the information about skills of workers and the quality of or accuracy of results in each task. They conducted several empirical evaluation on synthetic and real data sets. Here you see the real data sets in which they introduced several numbers of corrupted workers. So they modified data sets such that they introduce corrupted workers and then try to challenge each type of algorithms. So their algorithm is the red one, this one, and here. They try to challenge all the baselines in the proposed algorithm to provide information about error in the tasks given the number of corrupted workers in the data set. And we see that most standard approaches, so they have compared a lot of methods here, they fail to provide data with high quality or aggregate data with high quality when the number of workers raise slightly. And their methods, have much more better results. So it is a very fascinating result. So the key takeaway for us is that this algorithm may become a good method to aggregate results in the scenario of corrupted workers. So we definitely need to study this method on, for instance, if we talk about our platform or maybe some production pipelines of our clients, then we should consider such method or maybe include this method in our library. I guess we have one possible question if somebody wants to ask.
A question, please. Okay, so I will ask the question. I'm really curious about the scam detection and malicious annotator detection and crowdsourcing and research about it. And every time I read a paper on some malicious responses and so on, I am not sure if this model of malicious annotation and so on is, realistic. And when it comes to this paper, do you think if this model has some realistic foundations, or is it really this kind of annotation fraud observed in reality?
So as I remember, so right now I can provide the information with 100% of truth. As I believe, I guess they tried several types of frauds, if you want to call this, and they really see good results for that. But for sure, I believe that if we want to understand whether this algorithm is playable in our playground, so we need to investigate this algorithm on our own data. So the standard practice.
Yeah, and when it comes to the optimality, I understand this assumption. So if you assign the tasks randomly, so it shows the optimal result. But I think it's really important to remind us what to do with the. So what's the output of this algorithm? I'm not sure if I get it.
So the question is, what are the outputs? Let me move. So the output of the algorithm are these two vectors. So a vector of skills. So in terms of crowdsourcing, for sure, and in terms of the David-Skin model, the vector of skills. The skill is just the probability that the worker in this model provide correct answer or not. And the quality of the aggregated result of tasks.
Yeah, God, thank you very much. I think it's really worth reading again.
Yeah. No, for sure. I have the accepted invitation for this paper, so I believe that we will be able to talk and consider this paper much more deeper.
Yeah.
So let's consider the third paper. This paper is devoted to improving natural language processing tasks with human gaze guided neural attention. So as you can consider from the title, this paper in fact is devoted to a standard work, to the standard approach in NeurIPS papers. This work is devoted to neural networks, so popular networks connected with transformers. What are the key issues or problems that authors try to overcome by their work? So consider if we talk about supervision using human annotation, in computer vision, the authors claim that it is very easy to provide to attention network two types of data. The first data type is source image, and the second one is gaze data. Gaze data is just attention of humans where they pay attention on the image. So for instance, a heat map, and then make a prediction. But what about natural language processing? In fact, there are problems because there is not so much data or gaze data about texts. So there is a lot of corpora, but they usually contain very small amount of data about which point of text receive a lot of attention from a human and which one not. Much less. Okay, so the authors propose the following solution. The first contribution that they built a hybrid text silency model where they combine human gaze data and some cognitive model, also known as easy reader. This is the first contribution. And I just show how neural networks is complicated. You can see that they designed such a network which utilizes transformer layer, LSTM layer, and in this they plug into this network two models. The model that contains human gaze data, so labeled data, and some cognitive model. The second contribution of this work is that they provided joint training of the parameters of the whole network updated for a target task. So the architecture of such training is as follows. So they use a task corpus, they use this hybrid model, and they use this hybrid text silence model directly in the attention layer, and they train or learn the whole pipeline simultaneously. So it is the joint training approach here. And they show that on the example of two types of tasks, the first task is paraphrase generation measured by
Am I the only one who cannot hear the speaker now?
You are not.
So I'm not alone. Okay, so let's wait until Alexey restores his connection. I will reach him right now. Thank you. So I hope you can see me because The seminar is still going. Let's wait until Alexey restores his connection and we will proceed. Or we can switch to the second speaker if Alexey. Okay, he said me that he is reconnecting. Let's hope it won't take long. We have 6 papers today, and this is the third one. Okay, welcome back.
Okay, I'm
Yes, so welcome
yes,
back. Please share your screen.
problem. Okay. So can you just share me the last point that I presented?
So your last point was about the evaluation method. Yeah, this slide.
Okay, so you see that their method is very promising in comparison with respect to state of the art. What are the takeaways for us? First of all, you can see that even such very important field in machine learning for now, neural language processing, expect a lack of human labeled data. So this is in fact the opportunity to improve models just by bringing lots of data for them. So that means that community, NLP community, now does not understand the power of data excellence direction or power of data labeling instruments to provide lots of human labeled data. And for sure, if we talk about research, possible, I believe that possible future work for this study can be usage of human in the loop technology while training. So imagine that if we return back, so we consider this training, we see that we have a hybrid text science model that utilize human labeled signal, and we can provide human signal directly in this system. So apply active learning here as well. So I guess that's all about this paper. So if you have one question, I can answer, and then we will pass the microphone to another Alexey.
Great. So questions, please. Okay, since it's all about NLP, I have a lot of questions. I will focus on maybe one or two. First, I'm not sure if I understand this correctly, but when you showed the graph of human gaze, this is some kind of attention, right? And does it align in some sense to the attention learned, during the model training? So how does the human judgment and I mean human attention correlate with the machine attention? Have the authors discussed this? I didn't read the paper.
So in order to reduce possible wrong, the probability of wrong answer, let's devote this answer to the authors. So just maybe read the paper. I guess I will not provide with high probability maybe correct answer for your question.
I mean, every time I see some relationship between something that is learned by the machines and some that correlates with something that is perceived by humans, I always get somewhat excited or what. Like 2 years ago at ACL 2018, there was a paper, which was actually one of the best papers that received the award, that showed that when you use some neural model for dependency parsing, you receive some signals that correlate with the signals in the human brain from the electric encephalography. That shows that the parsing by humans is somewhat similar to the parsing by machines. It's always fascinating to look at these results. Okay, thank you very much. Any more questions? Okay, so I assume we can proceed to the next speaker, Alexey Volobuev. I think the stage is yours now.
Okay.
Sure. We can see you well. Thank you very much.
couldn't see me. Okay. Let me start with that paper. It's actually a paper from OpenAI. So you could guess it is about some application of GPT-3. Okay, we have a problem of text summarization. Given a long and complicated text T, we want to produce a shorter text capturing the essence of T. Standard approach would be to train a model to maximize Rouge score. What is Rouge score? It's actually a set of metrics. You might know about Blue score. It's more famous. Actually, it's quite similar to that. For instance, one of Rouge metrics is could be overlap of n grams from our text with those on references. In that problem, you have generated text and some human-generated references. This approach has some problems. One of the problems could be you're trying to optimize something very distinct from perceived quality of summarization. Okay, let us have an example of that problem. Long text is transformed into smaller ones. Take a look. Authors of the paper are using a TLDR dataset because it is known to be hard. It comes from Reddit, actually. Because it's hard, it needs abstraction-based approach. It means you are generating a summary text in contrary to extraction-based summarization algorithms, which just trying to assemble a summary from sentences already present in the text.
So yeah, but everybody was trying to read the whole text from Reddit, and well, I think the most concise representation was exactly below the example, like table 1 example of post samples. This is the shorter text we have here.
You mean human written or 6.7 billion human feedback model?
I mean the table caption put by the authors. Yeah, this is the shortest text here.
I see. Okay. So actually, there is a second dataset. It's called CNN DM, which comes from CNN News Network and Daily Mail. And it is much easier, so you can actually achieve superhuman performance with extraction-based models, which are very simple. It's just classifiers. So what is their approach to the problem? Firstly, we want to train a reward model which measures the quality of provided summary. How to train such a model? We have to collect a data set to train it. It's shown on the part 1 of the picture. Given a long text, you should generate or sample a number of summaries. Then you, for each pair, you task a human to evaluate which one he or she likes the best. Now we can train the reward model. It is trained for the objective written right here, it provides some estimation Ri and Rj and Rk, like in that picture, and it should minimize that loss written below. It's a logarithm of sigmoid of the difference. Then you can use that model to train the summarization model. Details are written in another OpenAI paper, Proximal Policy Optimization Algorithms by John Schulman and company. Okay. Next. Apparently, I'm just showing the slide again. Apparently, we are doing better than their standard approach. Actually, we are not providing detailed metrics because we are attacking them. We don't like, for instance, blue scores or okay. That's the idea. And actually, we have a quite interesting crowd-related pipeline. They would actually label that data set themselves if we had infinite time, money, or it would be interesting for them. But they had to ensure they are optimizing the pipeline so that outcoming labeling will be consistent with theirs. And what are the steps they introduced to do that? Interestingly, we have an instruction in the addendum to the paper. It looks cool, and the interesting part is, despite it is actually pretty detailed, we believe it is training that makes the hired labelers good. Good means that the labeling we produce is consistent with the scientists. And actually, we have some metrics like scientists are consistent 76% of the time between themselves on some hard data set. And actually, trained labelers are doing better in consistency with scientists. Okay, that's all for this paper. Do you have questions?
Yeah, we have some time for the questions. And does anyone have a question? Okay, I have a question then. I'm just, I'm not sure if I get it, but could you please go to the slide with the diagram with the approach that has 3 columns? I think, yeah, this one. So basically what they do, they obtain some pairwise comparisons between summaries, and they but I'm sure what's going on then. So as soon as you get these comparisons, you can provide a ranked set of some summaries. But what was done then? So I'm not sure if I understand why do we need this policy optimization part.
What? One second. You trade the reward model, yes?
Yeah.
It doesn't generate any summaries.
I understand, but I mean, so people judge the summaries, and then you train a reward model that uses the pairwise comparisons submitted by the annotator. But why do we need this? Why, when it's used then?
Why do we need? Because actually, it's much easier to compare summaries than what would be another method to train the reward model. You could use some metric on a scale from 1 to 10, for instance, to weight summaries, and you could try to predict that. And actually, that doesn't sound better or easier.
Okay, good. So this is the, well, this solution works well. Okay, cool. Thank you very much. More questions? I'm not sure if I hear more questions, so please go ahead and.
Okay. The next paper is Disentangling Human Error from Ground Truth in Segmentation of Medical Images. Okay, the problem of medical segmentation is, roughly speaking, to label lesion on some scan, some tumor or something like that. It has some distinctive traits. The cost of labeling is high because you are using trained professional medical workers like doctors, and it's costly. And actually, there is a lot of variability between them. Some are labeling more, some are less, etc. And in that work, authors assume that there is some gold standard labeling which we try to estimate given some human provided answers. So we have some images X and some estimated labels YN, and we try to estimate the ground truth. We use some probabilistic model, some simple assumptions on how the labeling process works. Their labelers are independent, and annotations of different pixels too. Actually, it's strange for me that annotations are independent, but so we came to the model 2. I mean that equation number on the line number 2, where we see a confusion matrix being multiplied by some ground truth distribution, which is interesting. Okay, they propose solution looks like that. We have an input image segmentation. One second. A segmentation model produces an estimated true label distribution. Well, okay. Annotation model produces estimated confusion matrices, and those estimations are coupled into estimated annotator distributions, which in fact could be plugged into the last functions and which could be optimized. To ensure the optimization problem is well defined, there is a regularization term in the form of trace of confusion matrices. Okay. We see that works quite well. That's all for this paper. Do you have questions?
Thank you very much. Yeah, questions. Questions, please. Okay, so is it correct? Let me ask the question then. Is it correct that this paper was all about evaluating? I don't remember how it's. Okay, it's called intersection over union between annotators, right?
Intersection of union?
Over union, so it's Jacquard metric. So because I'm trying to figure out what was the result of this paper. So when you annotate some medical images, it's extremely important to have well agreed responses by the crowd because you have some responsibility to carry, right? And so in order to provide consistent annotations of good quality, you need to properly aggregate those regions that people select, right?
Yes.
And how the proposed model can improve this, or does it even try to do that?
The thing is, we assume that there is a best of the best ground true label distribution, which is actually which is so good that the annotators would agree that it's good.
So it's like, you know, in David skin model, you have the latent label.
Yes.
This label is, you know, it's multinomial distribution. But in here, you don't have this, you know, these distinct labels. In this, in here, you have pixels.
Yes.
Which are selected, right? And this model allows you to aggregate the selected pixels from multiple annotators, right?
Yes.
I think, I mean, I've seen a lot of applications for this, and I think we should try running experiments on this model. It's really interesting. It's really important. It could be a breakthrough in region selection annotation. Okay, great.
Actually, that's quite interesting. Okay, the next paper, a topological filter for learning with the label noise. The problem is, as always, our labeling may be noisy. If D is our data, we can represent D as a disjoint union of D clean and D noisy, where D clean is data with correct labels and D noisy with incorrect ones. What if we could find D clean? Okay.
And what if we couldn't?
Yeah.
We are not lucky people. What happens then?
Actually, it would be good if we could. The idea is as follows. Deep learning models are actually good at finding noisy labels. Why? Because it is harder for them to learn those. Previous work is mostly concerned with exploiting uncertain labels. This work exploits embeddings. So let us stare at this picture for a moment. On the left side, labeled A, we can see Tisney projection of noise CFAR 10. It is the ideal representation, so it is actually really easy to spot the noise. It's inside the blobs. Actually, it is still the case for the picture in the center B, where the embeddings of some model trained presence of noise is given. So the main idea of their topo filter algorithm is to get some embeddings of some model, construct a KNN graph for each class where taking the largest connected component. It's on the line 11. And we are adding it to, we are stating that this data is mostly clean. We're taking the both largest connected components of each for each class, and then we're doing some something we call zeta filtering. It's just it removes outlying points which are connected to another class in some KNN graph with another K. So the idea is simple. Just embed, construct K nearest neighbor graph, take the largest components, do some filtering, and you're done. Do it iteratively, and you're good. Okay, experiments. We actually show that this works quite well on CFAR 10, CFAR 100, and then even on Clothing 1 million. Okay, that's all.
Yeah, so let me just ask you to remind me what is zeta filtering. I'm not sure if I remember this.
Actually, it's their zeta filtering. It's their idea. The thing is, we have constructed some on the step 12. We constructed some union of the maximal largest connected components. So we have a component for class 1, for class 2, etc., for class gamma. And we have some border frictions of those components. I mean, some points could be closer to other components than to
Yeah, so they like, you know, points in support vector machines methods, right? So some borders and stuff.
Something like that. And we are not sure if those points are reliable. We want to separate the clean data from the poisoned one. So we are throwing that away and hope that the next iteration of the learning, the training process will somehow decide if the data is really poisoned.
Okay, I still have a couple of questions just to, you know, make sure I understand the whole process, but I wish other members of this seminar ask also questions. Questions, please. Okay, so I have a couple of them. So the core idea of this paper is that we have received some annotations from the crowdsourcing platform, and now we want to distinguish the clean data from unclean data. And for that, we employ some machine learning technique. In this case, it's a neural network that shows which points are not reliable during training.
Yeah.
So, and if you repeat this process, you will eventually obtain the cleaned data C. My question is this process optimal? I mean, are there some theoretical guarantees that this process provides the quality of some epsilon bound or whatever?
We have some guarantees for binary classification task, and given the neural network has some additional properties which are actually hard to establish.
So, and when it comes to the initial problem formulation, well, is it correct that, well, when you perform crowdsourced annotation, you submit some data to the platform and you then receive labels provided by people? And when you want to, so you need to get the cleanest data possible, but you need the clean data for every item, for every task you submitted. And what happens in this case? So if I use this approach, is there a chance that I will get some tasks with no responses because they are unclean and unreliable in some way?
I didn't understood correctly, actually, your question. Could you please repeat?
Oh, yeah, sure. If you, well, usually you want to obtain responses for all the tasks.
Yes.
Because, well, you upload them to get the results. And if you apply this approach, is it possible that you will receive some tasks with no responses because they are unreliable?
Yes, it is. You should, in that case, you should probably relabel it, those tasks. Just send them again to the platform.
Yeah, got it. Thank you very much.
I don't think we. I don't know what will happen if algorithm finds a point which it labels as outlier and it is actually labeled correctly. I could easily imagine this situation.
Because every time I see a method that deals with, reliability in crowdsourcing or quality control in crowdsourcing or anything else, I always start thinking about, okay, this is a nice method. It should be useful for some class of problems, but what happens if you deploy it on a real platform? What happens then? Because sometimes you can get some coordinated malicious annotators. You can get weird instructions that affect they affect everything. Bad instruction is a really bad thing. And is it possible that if some people coordinate and do some bad things, is it possible to manipulate this approach using some reasonable and simple strategy? Do they have they provided some discussion on this topic?
We hadn't. We don't. The thing is, we think their approach will still work. Asked that question, but we hadn't checked, and I think it's actually possible to coordinate such an attack on that algorithm.
Cool. Thank you very much. Thank you very much. More questions? Okay, I hear no questions. And I think this was the last paper, right?
Yes.
Yeah, but if you want, we can say a few words about crowd science workshop, maybe 1 minute if you want.
Please.
Okay, let me show the screen. So we have also conducted crowd science workshop. There was a lot of talks here, so we invite you to look at previews or maybe live stream recording. In short, we had several invited speakers that are recognized experts in the field. We had 7 contributed works. They are listed there. Most of them have been published in our proceedings. The link can be found below. And also we have conducted very important and very valuable panel discussion where we tried to connect all stakeholders of crowdsourcing together. They are academia, representatives of global crowd platforms, data contributors and data requesters, and we discussed topics on perspectives of crowdsourcing and data labeling for machine learning, perspectives of trust, ethics. We have found a lot of synchronization among the panelists. We observed several crucial, important issues and points where further studies or further industry can on which you can work on and improve them. So in maybe nearest future, we plan to publish and present the things that we learned from our workshop. So stay tuned. And for now, you just can again look at our live stream recording and learn what we discussed and what we planned to do in future. So thank you. And now, Joyeux Noël. Happy New Year. Merry Christmas.
С Новым годом.
Yes. And
thank you very much for the presentations. I'm really glad to see all these papers. They can advance the quality of crowdsourced annotation quite in very useful way, and I think we should discuss them more and try them more and read more papers similar to them. Just to inform you, today is the last crowd science seminar that took place this year, so the next one will be in January 2021. I wish you best of the rest of the week and have a nice everything. Goodbye. That's it.
Thank you.